Welcome back everyone. So coming to the last assignment of this experiment 8, where we have to insert a Deadzone non-linearity in the system, and we'll have to study the effect of Deadzone in the system. And in this assignment, the value of Deadzone block already have suggested upper limit as 0.6 and lower limit as minus 0.6. So before we start to analyze what will happen if the Deadzone block is added in the system, initially we have taken a simple signal which is a sine wave. So double clicking on this, you can see the amplitude is 1. We have a Deadzone block here where I have set the value, the lower limit as minus 0.4 and higher limit as 0.6. Normally the value which is available in the Simulink library, it is minus 0.5 plus 0.5, very similar to the saturation block. So once I have set this, I wanted to simulate this. Double click on the scope block. So this is the scope output. So obviously magnitude of 1, this is the input or the sine wave actually, and the blue signal is the signal when the sine wave has been fed with the Deadzone block. Now you can see here some values has become 0, then having some magnitude, and this how this value has been calculated. So for this we have a written document. I have collected it from the net. It says that this output, the Deadzone block output, depends on the input as well as the Deadzone. It says that if the input is within the Deadzone, that is whatever the lower limit and higher limit we have set. So if my input is within that limit, that time output would be 0, and if it is greater than upper limit, then output would be output minus that upper limit. Similarly, it is applicable for the lower limit also. If the input is less than or equal to the lower limit, the output should be input minus the lower limit. So with this information, I wanted to explain this signal. So it was 1. If you remember, the higher limit has been set to 0.6. Zooming in, so you can see when the value of the input signal was in between the lower and the upper limit of the saturation block. So this is the value from 0 to 0.6. It is between the minus 0.4 and 0.6. That time, see, that time the value is 0. Next, what should be the next output? It is, I'm just matching from peak to peak. So this is highest value or highest peak was 1 magnitude. So 1 minus 0.6 is your 0.4. What about this lower side? The same thing. So lower magnitude or negative magnitude was 1, but the negative value was set as minus 0.4. You can see 1 minus 0.4 is 0.6. So that way the Deadzone works. So going back to the model, I have already created that. Just a quick check. What is the value has been set? Yes, start of Deadzone is minus 0.6 as suggested, and the end of Deadzone is 0.6. So okay, simulating this. So our XY graph has popped up, and we already have learned how to resize or reshape the axis of the XY graph. Now I wanted to show you the signal before the Deadzone. and signal after the dead zone. Minimize this. So this two. This is the signal before the dead zone block, and this is the signal after the dead zone block. So limit has been set 0.6, so it is above 0.6. So 1 minus 0.6, 0.4. It is 0.8. The limit has been set to high value was 0.6. So 1 minus 0.8 is 0.2. So this is the 0.2. So this is the effect of dead zone in this signal. Now already we have simulated. So moving quickly to the figure plot. So first one should be our error plot. Figure 2 should have error dot plot, and last figure is phase plane plot, that is error versus error dot plot. So this is the plot of dead zone, that is error versus, this is x-axis error, this is error dot, this is the phase plane plot incorporated with dead zone with the actual linear model. So this is the plot, and next we have, so this is the error plot and this is the error dot plot. Again, let me remind you that this block or this plot has been plotted with the structure with the array input. So that is the reason with respect to samples it has been plotted. So that much it was for the experiment number 8 assignment 4. Thank you.